Welcome to the 26th lecture of combinatorics. In the last class we were discussing the linear homogeneous recurrence relations with constant coefficients and order k. We saw a general method by which we can solve such recurrence relations provided the roots of the characteristic equation are all distinct. So, we saw that irrespective of the initial conditions we can get a solution for that using that method. The only difficulty is to solve the characteristic equation. If you want to get all the roots of the characteristic equation, it can be difficult, but of course if we have a reasonably small recurrence relation, a recurrence relation of small order, most of the time we can do that, but in the case of k being large it is questionable whether how will we get it. So, otherwise the rest of the things were working out, right, but that is all correct. And also see, once you see the technique, to apply that technique is quite routine. There is nothing clever about it, and one does not have to, you just have to remember the technique and you can apply it without much effort. Of course, so these recurrence relations themselves are coming from problems. So, the more difficult thing most of the time is to come up with the recurrence relation. So, we should not, when during this discussion we should not forget that is where the counting is actually involved. This is after the first processing and we get this recurrence relation, then we have this technique to solve. But of course, what we have to learn is this thing, otherwise the other part is usually depends on the problem, right. So, let us take some examples. We have seen some examples where the Fibonacci recurrence relations are coming earlier. So, now we will take some examples where some other recurrence relations results. So, for instance, you can look at this problem. Words of length n using only the 3 letters A, B, C are to be formed, subject to the condition that no word in which 2 A's appear consecutively is allowed. How many such words can be formed? I hope you understand the question. So, we have 3 letters A, B, C. We have to form words of length n. The condition is that there should not be an A like this in the word. For instance, this is not allowed, or this is not allowed. This kind of words are consecutive A's are not allowed. So, now how many words can be formed is the question. So, of course, obviously whether you have other methods or not, we are not interested. As of now we want to write a recurrence relation and then solve it to get the answer for this thing, right. So, what kind of recurrence relation can be written here? So, let the number of words be T of n, number of words satisfying these constraints of length n, which can be formed using the 3 letters A, B, C be this much, right. So, then consider an n length word. So, let us assume that n is greater than or equal to 3. Or n is greater than or equal to 2 would be enough, let us say. So, we will see 0 length words is equal to 0. One length word is just 3, right? This much is correct. So why is it so T? Because if we are not yeah, there is no 0 length word at all, and one length word you can either have A, B or C, fine. But 2 length words, if you ask, that should be how much? So AA is not allowed, any other 2 combinations are allowed, right? So that is, you can have A, B, A, C and B, C. Sorry, B, C, B, A, B, C, B, B, that is also allowed, and C, A, C, B, C, C. These are the 2 length words, right? Well, there are a lot of them, of course. 1, 2, 3, 4, 5, 6, 7, 8 of them are there. Out of the 9, see, we have 3 into 3 2 letter words. Out of that, A should be removed. That is why 8 is coming. But anyway, so we do not need T of 2 here. We will get it using the recurrence relation. So we will just use these 2 because these 2 are very easy. Now how will you, suppose there is, we are thinking of n length words. So the first letter can be A, B or C. Let us say it is either B or C. Suppose this is not A, then we do not have any restriction on this part. This is the n minus 1 length part, right. So if it is either B or C, then we can just form all the T of n minus 1 possible words here. So that is 2 into T of n minus 1. Okay. On the other hand, suppose it is A here, suppose A is sitting here. See, this 2 comes because we have either B or C for this case. Suppose A is sitting here, then there is a constraint that here we cannot have any, right. So here we cannot have any, that means here we have B or C, 2 choices here, and then this portion we can fill in any possible way, that is T of n minus 2 ways, right. So that will be 2 into T of n minus 2 total. So once you fix A here, here we have 2 choices only, 3 choices are not there, B or C, but for each choice we have T of n minus 1, T of n minus 2 ways to fill this portion, right. So that is this plus this. So we get T of n equal to T of 2 times T of n minus 1 plus 2 times T of n minus 2. This is the recurrence relation which is coming from here. So note that even when n equal to 2, this argument works, because if n was equal to 2, of our argument told if it is B or C here, this is T of 1 ways you can fill it, that is 3, right, in 3 ways you can fill it. If it was A, then here we have only 2 choices, 2 into T of 0, right. Okay, that means we have to set it as 1 here, correct, because we have how many 0 length words are there? We should put it as 1. So the earlier it was 2 into 3 plus, now it is 2 into 1. So, total 8, correct. So, yeah, T of 0 should be set as 1 for this purpose. See, of course, how many words of length 0 are there? That is of course, see, if you ask like that, so yeah, it depends on our requirement. Here our requirement tells us that it has to be 1. So, or otherwise we should have started with T of giving T of 1 and T of 2 and then using trying to set up the reconciliation, but this is okay because we just define T of 0 is equal to 1, right. Now what we do is we try to solve this. T of n equal to 2 times T of n minus 1 plus 2 times T of n minus 2 with the T of 0 equal to 1 or T of 1 equal to 3. These are the initial conditions. We get the characteristic equation first. So, without much effort we can see that it is x square minus 2x minus 2 is equal to 0, right. X square minus 2x minus 2 is equal to 0, and we can solve it using the method to solve the quadratic equation, minus b plus or minus b square. So, that is 2 plus or minus 4 plus 8 divided by 2. So, this is 2 plus or minus 2 into root 3 by 2, right. So, we end up getting two solutions here. The one is 2 plus root 3, sorry, 1 plus root 3, 1 plus root 3, and the other is 1 minus root 3. These two solutions will come, right. So, these are the possible values that we can give for Q. You remember from the last class. So, we were calling Q as the possible solutions. So, therefore, we get that some C1 and C2 we can select such that C1 into 1 plus root 3 raised to n plus C2 into 1 minus root 3 raised to n is a solution for T of n. What you should remember is, if I just substitute 1 plus root 3 raised to n for T of n, this recurrence relation will be valid because 1 plus root 3 is a solution for this thing, for the characteristic equation. Similarly, if I substitute 1 minus root 3 raised to n for T of n, then this recurrence relation will be valid because 1 minus root 3 is also a solution for this recurrence relation. And for any constant C1 times 1 plus root 3 raised to n is a solution for T of n. Any constant C2 1 minus root 3 raised to n is a solution for T of n, right, and so on. But yeah, this will be valid for n greater than or equal to 2, right. But yeah, but this only satisfies the recurrence relation if we also have to satisfy the initial conditions, namely T of 0 equal to 1 and T of 1 equal to 3. If this is to be satisfied, we have to carefully select the C1 and C2, right. How will we select it? We just put n equal to 0 and write down what will happen. So, C1 plus C2, because putting n equal to 0, so this will become 1, this will become 1, C1 plus C2 is equal to 1 is what this says. T of 0 equal to 1 implies this. And similarly, it's okay, C1 plus C2 equal to 1. Now, when I put n equal to 1, I get C1 into 1 plus root 3 plus C2 into 1 minus root 3 equal to 3. So, now we have to solve for this as we have elaborately explained in the last class. This will always have a solution, right, because we had distinct roots here, 1 plus root 3 and 1 minus root 3. So, and we just have to solve this thing, we know how to solve it. So, the answers will be answers will be C1 equal to, I am just copying, C1 equal to 2 plus root 3 by 2 root 3 and C2 equal to minus 2 plus root 3 by 2 root 3. These are the solutions we will get for this thing. And now we can substitute for C1 and this will work for n greater than or equal to 0. Right. This will indeed work for n greater than or equal to 0, because now this and this is satisfied. For n greater than or equal to 2, this equation was satisfied for any C1 and C2. So, now we are giving special values for C1 and C2, right, which also satisfies this, that is all, right. So, now everything is will be satisfied. So, this is the way we solve it. Now, next one, so we will anyway. So, we can take any number of examples of this sort, right. This was also the problem, there was a problem, and this problem was formulated using the recurrence relation. I mean, the counting, how many words can be formed. We first noted that it will be the solution of the recurrence relation T of n equal to 2 times T of n minus 1 plus 2 times T of n minus 2 with some initial conditions, and we solve for it. Of course, so so we have to in general, usually there will be a problem which we have to be converted into a recurrence relation, then only we will solve the recurrence relation. But again, we can discard that first part for the time being. We can concentrate on just the second part, because that is what we have to now study, though it is a little dull. Once you learn the technique, it is just routine, there is nothing much to think, but still we have to know that. So, therefore, we quickly cover this material. So, my coverage of this material is going to be quite brief. I am following the book of Brualdi, which is mentioned in the first lecture, Introduction to Combinatorics. But in the book Grimaldi and Ramana, so you will get a more extensive treatment of this topic, though we are covering all the essential things, just that in the second book Grimaldi and Ramana, so it is more elaborately treated with more examples, more in a more detailed fashion. So, the student is advised to read that presentation once. But I am following this presentation because this is brief, and still it has all the necessary things. So, that is why, because we want to finish off this portion fast and get into something else, which is where we can discuss more, because this is in general we just have to know how to do this thing, because the rest of the things I believe that is routine. So, that is why I do not want to spend too much time on this thing. So, now the second thing we want to discuss here. After that distinct root case of the characteristic equation have all roots distinct. Now we will consider the case when all the roots are not distinct. So then you can note that this Hn equal to C1 times Q1 raised to n plus Ck times Qk raised to n need not be a general solution for the equation, in the sense that it will be a solution of course by the argument, because Q1 raised to n, Q2 raised to n, all those up to Qk raised to n, they are all solutions. Then we can also combine it. But the only thing is not the general solution, in the sense that for some initial conditions we may not be able to find the correct coefficients, because whichever coefficients you give, it may not work for certain initial conditions. So those of you who can who are quick can see from this itself. For instance, if Q1 is equal to Q2, that means Q1 repeats, then this what Hn equal to C1 times Q1 raised to n plus C2 times Q2 raised to n up to Ck times Qk raised to n will simplify to C1 plus C2 times Q1 raised to n plus C3 times Q3 raised to n plus and so on. So that means we lost a constant, though we are writing C1 plus C2, it is only one constant there, right? C1 plus C2 we do not have much information about, so that does not help in which way we split that C1 plus C2, right? It is only one constant, C1 plus C2 has only become one constant. And then when we write all those system of equations, we will have the number of variables will be less compared to the number of equations we write. We know that, yeah, so from linear algebra, if you have done linear algebra, you should know that there is some trouble here. You may not get solutions in some cases. Some cases you will get, some cases you may not get. But rather than depending on your knowledge of linear algebra, what I will do is I will give a small example and make you understand this point. But those of you who know about all these things need not worry too much. So it's very clear, right, that it will not work out. You should remember the discussion we did in the last class. You should try to repeat those arguments and see why it is failing. For instance, when you form those equations, so why we have see, you write k equations and we have only less than k variables there, right? So we have some trouble there. So for instance, let us look at this recurrence relation, Hn equal to 4 times Hn minus 1 minus 4 times Hn minus 2 for n greater than or equal to 2. Hn equal to 4 times Hn minus 1 minus 4 times Hn minus 2. This works for n greater than or equal to 2 only. Now your characteristic equation is going to be x square minus 4x minus 4 is equal to, sorry, plus 4 equal to 0. This is the characteristic equation. Now this is what, x minus 2 whole square equal to 0, which means x equal to 2 is the only solution. So if you had used the method to solve the quadratic equations, you would have got x equal to 2, x equal to 2 times, right? The root repeats 2 times. Oh, for instance, that p square minus 4 I see here, for instance 4 square minus 4 into 4, that is becoming 0. Therefore, yeah, we do not have 2 roots, it is just that yeah, minus p by 2 will be the only solution we get there, yeah, if you use that method, right. So, otherwise we say that here the yeah, the solution x equal to 2 has multiplicity 2 here. Now, what do we mean? So, we can indeed say that 2 to the power n is a solution, C1 times 2 to the power n is a solution. If you want, C2 times 2 to the power n is also a solution for any constant, but that does not help, because this is only C1 plus C2 times 2 to the power n, which is some C dash times 2 to the power n, right. So, this will not help, because splitting a constant into 2 will not help. So, why will it not help? Because put n equal to 0, we have two initial conditions. So, we will have something for yeah, h0 and h1, right. h0 is equal to something, h0 is equal to something, let us say h0 is equal to 1 and h1 is equal to something. So, we will decide this something, so that we will not get the answer. So, put h0 is equal to 1, put n equal to 0. So, this gives us c dash into 2 raised to 0, that t dash is equal to 1, c dash equal to 1, right. Now, when you this one, right, suppose h1 is equal to some a. So, put n equal to 1, we will get c dash into 2, that is 1 into 2 is equal to 2. So, if this a was not equal to, suppose I take 3 here, a equal to 3, then 2 won't be equal to 3, right. So, in other words, first I selected to match the value of h0, we already selected c dash, and we have only that constant, that only one constant we have. That constant, if by luck, if this was also 2, it will work out, but if it was 3, if it is something else 4, it won't work out, right, because this is the whichever constant is here, it has to be 2 times c dash, right. So, it won't work out. So, that is you can see that when there are repeated roots, it is not working out, right. So, it may not give a solution. So, what we do is, so there is a technique to circumvent this. So, if a possibly complex number q is a root of multiplicity s, that means that q repeats s times of the characteristic equation of a linear homogeneous recurrence relation with constant coefficients, then it can be shown that each of hn equal to q raised to n, hn equal to n times q raised to n, hn equal to n square times q raised to n, hn equal to n raised to s minus 1 times q raised to n is a solution, and hence hn equal to c1 times q raised to n plus c2 times n q raised to n plus c3 times n square times q raised to n plus cs times n raised to s minus 1 times q raised to n is a solution for each choice of the constants c1, c2, cs, right. Irrespective of the constant c1, c2, c3, cs we take, this will be a solution also. So, in our case, previous case, we had 2 coming 2 times. So, we could have taken, we say that 2 raised to n is a solution, and also n times 2 raised to n is a solution, right. So, this is yeah. Hn 4 times hn minus 1, 4 times hn minus 2. So, we have n raised to 2 raised to n is equal to 4 into n into right, 2 raised to 4 into, here we say 4 into n minus 1 into 2 raised to n minus 1 minus 4 into n minus 2 into 2 raised to n minus 2. So, we can cancel 2 raised to n. So, this n equal to 2 into n minus 1 minus n minus 2. So, that is n equal to n. So, minus 2 plus 2. This is true. What have I done here? So, we have already checked that 2 raised to n is a solution for this thing, because the characteristic equations has root 2 as a root of characteristic equation. So, it should be satisfied definitely. So, now we are saying that even this will be satisfied, which I just substituted it. So, and so what is happening here. So, n into 2 raised to n I put for h n, here 4 into n minus 1 times 2 raised to n minus 1 is put, and here it is 4 into, so n minus 2 into 2 raised to n minus 2 is put, and I verified that it is indeed satisfied. You can check that for the general case of h n equal to a 1 h n minus 1 a k h n minus k, this n times q to the power n, where q is a solution of the characteristic equation, will indeed work for this also, right. So, let us leave it to you to verify that. And now not only n, because it depends on how many times your solution repeats. If it repeats 2 times, we just take q to the power n is a solution, and n times q to the power n is a solution. If it repeats 3 times, then q to the power n times q to the power n, and n square times q to the power n is a solution. You can check it. So, if it is in general s times, then q to the power n times q to the power n, and n square times q to the power n, all the way up to n to the power s minus 1 into q power n minus 1. These are all solutions. So, if these are all solutions, we know that we can also combine them, because this satisfies the recurrence, this satisfies the recurrence, this satisfies the recurrence, and this satisfies. Any multiple of this multiplying by a constant is not going to disturb that. For instance, that will be still satisfied. For instance, say c times n to the power I into q power n, for as far as I is in between 1 and 0 and s minus 1 will again satisfy this, that we know, and we can add them together, and then their combination, their sum also will satisfy. So, we can infer that c1 times q raised to n plus c2 times n times q raised to n plus c3 times n square times q raised to n plus cs times n to the power s minus 1 into q raised to n will also be a solution for the recurrent solution. So, this is a solution. And this will work for any choice, as obviously for any choice of C1, C2, C3 and Cs, this will work, right. Now, we can, so this is about the same Q repeating, right. So, now of course, when I solve the characteristic equation, it may so happen that there are t distinct roots q1, q2, say up to qt, but its degree k can be bigger than t. So, q1 may be repeating say s1 times, q2 may be repeating s2 times, and q3 may be repeating s3 times, and qt may be repeating st times, where s1 plus s2 plus st is going to be your k, degree of the polynomial. So, here of case, so now what we do is, for each qi here, we can have a part like this, right. For instance, for any qi which is satisfying, we can have a part like this, and let us call it as, so that particular part as h I of n, right. And then it is clear that this h I of n, this one c1 raised to qi raised to n plus c2 into n times qi raised to n plus c3 into n square times qi raised to n plus cs into n raised to s minus 1 times qi raised to n will satisfy this. The general solution of the recurrence relation will be the sum of all these parts. There are t parts because there are t distinct roots, and each had si here of case. So, here I had to put cs si minus 1, right. Here we will have to say si minus 1, because now s is not, for qi it is si, right, si minus 1. Now, you sum up hn equal to hn of 1 plus h2 of 2 plus, sorry, hn of 2 plus hn of t, right. If you add up all these things, you will get it. So, I can maybe write the general solution will be hn is equal to q1 raised to n plus, so here it is some c11, right, plus n into q1 raised to n plus c1 2, maybe this can be c1 c2 1 into n square into q1 raised to n and so on, plus cs raised to 1 n raised to s minus 1 into q1 raised to n, plus then q2 raised to n plus c21 n q2 raised to n plus, sorry, this is c1 raised to 2 c2 2 n square into, sorry, so here coefficients are to be, we will say c1, this is c2, this is c3, and this is cs, and we have 1 here to indicate it is the first one, right. C1 2 q2 raised to n up to cs 2 q2 raised to, so this is n raised to s minus 1. So, okay, this is s1, this is s1, this is 2 minus 1, q2 raised to n, and so on. The lastly we have c1t qt raised to n plus cst raised t n raised to st minus 1 qt raised to n. This will be the general solution. That is what we get. Of course, this is I have added all of them together and written. Now we can, of course, this is the way we have to do. So we can take an example and see what will happen. So solve Hn equal to minus of Hn minus 1, Hn equal to minus of Hn minus 1 plus 3 Hn minus 2 plus 5 Hn minus 3 plus 2 Hn minus 4, 2 Hn minus 4, and this will work only for n greater than or equal to 4. And we have some initial conditions 1 0 1 2, 1 0 1 2 for H0, H1, H2, H3. These are the initial conditions. The first 4 values have to be given, and this for n greater than or equal to 4 onwards, this will work, this recurrence relation will work. The characteristic equation is x raised to 4 minus, sorry, this plus x cube minus 3x square minus 5x plus 2, sorry, this is again minus 2, minus 2 equal to 0. We are taking all these terms to this side and equating to 0 and cancelling the n raised to 4 power x to the power n raised to 4 or q to the power n raised to 4 and writing the characteristic equation, right. Now you have to solve this thing. So if you solve it, characteristic equation the characteristic equation is will have roots, so x equal to minus 1 minus 1 minus 1, 3 minus 1 repeats 3 times and 2. These are the solutions of the, so the roots of the this characteristic equation, x equal to 5x minus 2 equal to 0. The roots are minus 1 minus 1 minus 1 and 2. Minus 1 has multiplicity 3 and 2 has multiplicity 1. Now we can write the part h. So the let us say we see that q1 is equal to minus 1, its multiplicity s1 is equal to 3, q2 is equal to 2 and your s2 is equal to 1, its multiplicity is 1. Now the part corresponding to this, in the general solution, the part corresponding to this, it will be h1 1, this is the way you write, right. First minus 1 raised to n, so we will have a constant for it, C2 times minus, sorry, n into minus 1 raised to n plus C3 into, because 3 there are 3 terms, E3 into n square into minus 1 raised to n. And for this portion q2, so h1 h2 of 2, sorry, this is hn of 1, this is the way you wrote, hn of 2 is equal to just 2 to the power n, right, c times 2 to the power n, or we can write some other constant, say d times 2 to the power n. So we can, the general solution, we will add this and this together, right. So we will sum up this part and this part, these are two different parts and add together, right. So, we will get Hn equal to Hn1 plus Hn2. So, this is minus 1 raised to C1 raised to minus 1 raised to n plus n into C2 into n into minus 1 raised to n plus C3 into n square into minus 1 raised to n plus d into 2 raised to n. This is what we will get. Now, we have to find the values of C1, C2, C3 and D, so that the initial conditions are met. The initial conditions were this: H0 is equal to 1. From that, what will you get? Put n equal to 0 here, all this will become C1 plus C2, C3 will go away. C1 plus D equal to C1 plus D equal to right. Yeah, C1 plus D is equal to 0. This is what, sorry, that is 1. So, H1 equal to 1. So, go once again, go back to the initial conditions. H0 is equal to 1, H1 equal to 0. Let us say, because we have only 12 more minutes to go. So, we have to substitute for n equal to 0. So, then n equal to 1 we have to substitute, we will get something from this thing, and then yeah, substitute for each of them and solve. That is what we want. Of course, it is not worth solving it completely. So, I leave it to the student. This is a routine task, there is no new things involved in it, right. We just save some time by just skipping it. So, we will go and look at the next section, non-homogeneous recurrence relations. What is this non-homogeneous recurrence relation? See, in the previous case we were considering the homogeneous case where that Bn part was 0. Again, if you go back to our the way we wrote the recurrence relation, it was h of n equal to C1 times Hn minus 1 plus Ck times Hn minus k. This was the homogeneous thing. In the non-homogeneous case, we will also have a plus Bn here, right, this one plus Bn here. This was 0 for homogeneous case. In the non-homogeneous case, Bn will not be equal to 0, right. So, we can give an example. So, simplest, see, k equal to 1 case, the order 1 case, and one of the most famous examples, the Tower of Hanoi problem. Tower of Hanoi problem. What is this Tower of Hanoi problem? So, we have this pegs, right. So, so it is we have a peg here. In the peg we have some discs of decreasing size. I am not good at drawing things. So, let us assume that there are discs 1 here, 2 here, 3 here, like this. So, it is a peg here. Then we have another peg here, this is peg number 1 and there is a peg number 2. So, we want to move all these discs to this, right. We can use a third peg as a temporary place to keep the disc. We are not supposed to keep the disc on the floor, it can stay only in these pegs, otherwise it will get destroyed, say. But there is another problem, you cannot put a peg here like this, and on top of that we cannot put a bigger peg, maybe the smaller peg will bigger disk, right. This is not an allowed thing, maybe this will get damaged because of its weight or something like, or in other words what we say is we can only keep the disk on the peg in descending order of their sizes, means the biggest one should be in the lowest position and so on. So, you can never put a bigger disk on top of a smaller disk, right. And then how can you move this disk from one peg to the other? So, one may wonder, is it possible at all? So, we can just take some simple examples. You can easily see that you can do it somehow, because you have 3 pegs, right. There is a temporary place to put, right. So, one possibility, for instance, if you had only one peg, there is nothing to worry, because you just take the peg and put it. But there were there were only one disk, it is quite easy. But if there are 2 of them, then what I do is say, let us say this is A, this is B. What I do is first I take this B, right, from the peg and transfer it to the third one. So, I keep the B here. Now, I can move A to here. So, A will be put here and then B can come here, right. So, this is the way one can do, right. If there are more of them, you have to be more careful. If there are 3 of them, A, B, C, then first I will move C here, then I have to move B here, right. Then also okay, first I have to move C here, and then I move B here. I will say, for instance, if it was A, B, C, C being the smallest, what I do is I take C here first, then I take B and put it here, then we can have C on top of this. So, it should have been other way. So, first C should go here, B should go here, and then I can put C from here to here, and then A can come here. So, this is the way we should move, right. Now, what should I do? I should take back C here, right. C will come here and then B can be moved here, B, now C can be moved here. So, these are the kind of movements we are looking for. One has to be clever, so that we never end up putting a bigger disk on top of a smaller disk. The question is how many moves are required, right. So, the number of moves required can be modeled using a recurrence relation. So, this is the way we do it. Let T of n be the number of moves. So, it is clear that so from this first peg to the, if you want to move the lowest disk, that means the biggest one from here to here, this should be empty at some point of time, because it should go here, and all these remaining n minus 1 disks should be moved to here, right. They should be in the proper order, right, and this takes T of n minus 1 steps in whatever way you do, and then you can move it to here in one step, right. So, this is a recurrence relation. The first you move all these n minus 1 disks which we see on top of the biggest disk, above the biggest disk n minus 1 of them, this should be moved to here in some way. You can use this intermediate peg here. The role of this first, second, third peg will change, because now the third peg will take the role of the second peg, right. And now we can move this down, that is one more. And it is very clear that you need this much also, right, because at some point of time we should have this situation that this entire thing has gone here and this is here and this is here, then only you can move. So, therefore, this is the number of moves required. And how will you solve it? Oh, sorry, this is so of course then what happens is we should also bring it back. So, therefore, that is 2 into t of n minus 1 plus 1, 2 into t of n minus 1 plus 1. This is the number of moves required. So, the first we transfer it, we have to come back to the initial situation, right. We should get back to the first spec, right. That is why 2 into t n minus 1. Now, t of n, so we have because you are familiar with this recurrence relation from your algorithm class and all. So, we know that see this solution is usually, so you write it as t of n this one, then what you do, you substitute it 2 into 2 of t of n minus 2 plus 1 plus 1, this will give you a 4 times t of n minus 2 plus 2 plus 1 and so on, right. So, this will essentially lead to finally this unrolling will lead to 2 to the power n minus 1 into t0 plus t of 0 plus 1 plus adding together all these things 2 plus 1 up to here, and this if there is 0 moves, there is nothing to do, therefore, it is just t of n minus 2 raised to t of n minus 1 up to 2, and this we know is 2 to the power n minus 1, right. This is the answer for this. How did we do this thing? We just unrolled, right. So, we wrote substituted and then we finally came to the last. So, in n minus 1 steps, so starting from n minus 1 we ended up with this, right. And so, that is why we could do this thing, but here the thing worked because finally we got this sum and we could sum it up, right. And that depends on whether we can do that sum or not. We will discuss further on this non-homogeneous regression in the next class.